So last time we talked about finding um, compositions, phases present, and the mass or weight fractions of the phases that were present. And we did this for the isomorphous system. This copper-nickel system was our example. And so if you don't remember that, I advise you to go back and take a look at that video. And then before you continue with this one. All right, so on this one, we're going to go ahead and we are going to look at again, the same type of problem, but we're going to do this now with this eutectic system, and then we're going to work up to doing a little bit more of a complicated problem. So let's say that we have the lead-tin system. By the way, the lead-tin system used to be the solder of choice for your copper plumbing. We don't use it anymore because, of course, the lead. But the reason why this was a good solder is because it's a eutectic system. And so for a good solder, you want something that's easily meltable, and you'd like it to melt at one temperature, where most alloys, of course, will melt over a range of temperatures. We kind of talked about that. So in the eutectic system, you've got this nice eutectic point where you can get, where you've got an alloy, so you can get solid solution strengthening, but you can also melt it, and you can melt it at a lower temperature than either component, so it doesn't take as much energy, and it makes it relatively easy to melt. And so these eutectic systems are nice for solders. All right, let me get off my little sidetrack there. Let's get back to the problem. So we're going to look at a 40 weight percent tin, 60 weight percent lead alloy. So when these compositions are given, just be careful to double check your axes, because you're not always going to be given the axis first. So in this case, we are. This is weight percent tin, and we're given the weight percent tin first. So 40 is the one we're looking at. Okay, but that's not always the case. So we want to go, once we do that, we want to make sure that we go ahead and mark that on the diagram so that we know where we're looking. And then the next thing we need to know is our temperature, 150 C. So there's our 150 C. So we're sitting right here at this point B. So we're in the two-phase region, alpha plus beta, and we will have an alpha plus beta, and the alpha, right, if we draw now a tie line at 150 C all the way across my region that I'm in, then I will get the composition for the alpha here at 11 weight percent tin, and therefore 89 weight percent lead. And then on the other side of the tie line, we get the composition of the beta, which is 98 weight percent tin, therefore 2 weight percent lead. So we did that before as well. So same procedure. And now what we want to do is go ahead and look at the mass fractions. So how much alpha and how much beta do I have as a fraction? So first thing I'm going to do is go ahead and I'm going to trace out my tie line across there just to make things a little bit easier for myself. This is just a good habit to get into. And so I've traced it out. I'm going to go ahead and bring my tie line out of the diagram, and I'm going to go ahead and I'm going to label everything that I know. So one thing I want to do is make sure that I mark where my endpoints are for my two phases. So the alpha is over on the left side, the beta here is over on the right side. And I've pulled off the composition of the alpha, the composition of the beta, and the overall composition of our alloy. And above this, I already have the answers. We'll go ahead and we'll get to these, but this, this fractional part on the left side is 33%, and this fractional part on the right side is 67%. And so again, they have to add to 1 to equal the whole tie line. So those are going to be actually my two answers for the mass fractions of the two, alpha and beta. But what I have to remember is which one's which, right? And remember, this is where the inverse rule reminds me that if the alpha is on the left side, then this number over here on the right side is my weight fraction of alpha. The beta now is over here on the right side, and so the left side piece over there then is my weight fraction of beta. And so that's how I remember which one it is, the inverse lever rule. And that's the only time, that's the only case where the inverse lever rule is used in these types of problems. All right, so that's actually my answers. How did I actually get the numbers? Well, at least once I got everything labeled, right, normally then we would go ahead and calculate those fractional pieces. You know, I can eyeball them, and they look like they're about 1/3 to 2/3. That's kind of my check. But then I've got to go ahead and calculate them. So that right side piece has a length of 98 minus 40, and the total tie line length there is then 98 minus 11. That's 0.67. And the beta, fractional amount of beta, which we said is over here on the left side, that length is 40 minus 11. And then again, the total tie line length is 98 minus 11, and that will give me 0.33. So that's how I get it. So there's an equation again in your book that is set out that'll tell you to use the composition of, so it'll say something like C0 minus C alpha over C beta minus C alpha, and that'll be the fractional amount of beta in that particular case when your problem is on the left side of the diagram. And then they'll have another equation for the amount of beta if your composition happened to be over on the right side of the diagram, right, left and right relative to the eutectic point. So you got all these equations running around, and it's a complete mess, I think. All you have to do is this inverse lever rule. Trace out your tie line, pull it out of the problem, label it, and then pull off those fractional pieces. Always works. It doesn't matter where you are on the diagram. All right. So let's look at another type of problem that's related. And this one says that you've got a 30 weight percent tin. So again, we check. This is tin down here. So 30 is where we want to be. It says we're heated into the alpha plus liquid phase region. All right, so my alpha liquid phase region is here. So it means my temperature then is somewhere between the 183 and about right here. That's when I would leave this alpha liquid and I'd be all liquid, say if I move up here, right? Because I have to exist on this line because that's my composition. All right, so I'm going to be somewhere in between there, and it wants to know what the temperature of the alloy is. Where am I between those two markings? And what I'm given is that those fractional amounts, the mass fraction of the two phases, are 0.5. Both of them are 0.5. So I've got 50% alpha solid and 50% liquid. Okay, wants to know where I am. All right, so at first it seems like we don't have quite enough information, but if we think about this, and we can just estimate this problem. Let's just go ahead and pick a temperature and draw a tie line on the region and pull off some values. Okay, so let's say we picked a temperature of 200. Well, if I went and picked 200, I can see here my tie line, right, is sitting right here now. Well, I don't have to even pull off the values of these endpoints because I can see that this length here is definitely not the same as this length here. And this looks more like a 2/3 to 1/3 ratio, not 50-50. So that's definitely not right. All right, so what can I do? Well, let's go ahead and move our temperature up a bit. Okay. Now I've sort of exaggerated, I've gone way up. Of course, now that I'm too high in temperature. So now I've got this length versus this length, right, for my tie line that's sitting right in here like this. All right, now I've gone too far the other way. Right? This one looks like maybe it's about 0.4 and maybe to 0.6 or something. So let's go ahead and drop the temperature. So what you would do if you're working on this problem yourself, you just put a ruler on here and just slide the ruler back and forth until you see it intersect these two ends and these two pieces look 50-50. Okay? So I'm going to go ahead and drop that temperature down a little bit, right about there. So that looks about 50-50 to me. If we check down at the bottom, you can see, here we are at 30, and it looks like I've got about 10, 12, say, difference here, and it looks like I've got about a 12 difference here. So that looks pretty good. So this is maybe 42, and this one over here is maybe 18, something like that. Maybe the distance is more like 13 apiece, but you get it. So you pick those points off, and now if I was to plug these values in to my weight fraction equation using my inverse lever rule, I'd see that I get about 50-50. So it looks like my answer is something like 225 degrees. All right? So that's how you do that one. And then the compositions of the two phases. Remember, the alpha composition is over here. So composition alpha is, say, 18 weight percent tin, so 82 lead. And the beta is over on here, which we said was 42 weight percent tin plus 58 weight percent lead. All right, those are our two answers. So I'm going to stop this one here, try and break up the this chapter into a bunch of smaller lectures. The next time we're going to go ahead and take a look at the microstructures that you can get in the eutectic system.